Hi, welcome back again to the lecture on kinematics. If you still can recall, during the start of this lecture series, we mentioned that there are two types of motion that we're going to study, namely linear and angular motion. And we have covered the linear aspect to date. And just to refresh your memories, during the linear motion lecture, we understood that there are basically four key quantities or parameters that we can use to describe the kinematics of a moving body. There are time, displacement, velocity, and acceleration. And all these four key parameters are embodied in a velocity time graph. For the vertical motion, linear motion, we mentioned that the formulas used are exactly the same for the horizontal, with the exception of the acceleration a, whereby a is taken to be 9.81 meter per second square, and when it's moving up, the sign convention for a will be negative, and when it's moving down, it is taken as positive. So now we'll start our study on angular motion. As the name implies, angular refers to rotary or circular motion. As such, the body of interest moves around in a fixed radius about a certain point O. In the same context, taking me for example, let's say at time t I'm here, I move in an angular fashion about the point O at the constant radius r. Now, for this type of motion, do you think linear displacement S is a good descriptor for the angular displacement that I've just covered? Take a minute to think about this. Can you think of a better parameter to better describe this peripheral displacement that I've covered? Meaning at certain point t, this parameter is able to pinpoint exactly where am I and how far have I traveled in the angular sense. Do I hear someone mumbling angle? Excellent. Yes. Angular displacement is best described by the angle theta. For example, when we tell others that I'm currently at theta equals to 90 degree, let's say, they will know exactly when am I. I'm at the y-axis. If theta is equals to 720 degree, they will know that I've traveled 2 rounds around the angular path. And the SI unit for theta is radians. So now that we know for angular motion, displacement is described by theta with unit radians, how fast a body actually circulates around the peripheral motion will be described by the parameter omega, which represents angular velocity, and it has a unit of radian per second. And in the same spirit, how fast this angular velocity changes with time, we use the parameter alpha, which represents angular acceleration with a unit as radian per second square. Let's refresh what we learned in the linear kinematics. In the linear kinematics, we learned and was introduced to these four kinematics parameters: time, displacement, velocity, and acceleration. So for angular kinematics, these are the four parameters or quantities that we will use in this topic: time, angular displacement, angular velocity, and angular acceleration. So now that we have a clear understanding on what angular motion is all about, I think it's a good time for us to do a quick comparison of the different representation used to describe the quantities in linear and angular kinematics. So for time, Linear, we are using t with seconds as its unit, and this is the same for angular. For linear displacement, we are using s to represent linear displacement with a unit of meters. For angular displacement, we use the symbol theta, and radians is its unit. For linear velocity, we are using v with meter per second, and angular velocity, we are using the symbol omega, radian per second as its unit. Last but not least, for linear acceleration, we use the letter a, meter per second square, and for angular acceleration, we are using the symbol alpha with its unit as radian per second square. At this juncture, I think it's good to refresh the relationship between degrees and radians, because in kinematics, radians are used for analysis. So 1 revolution is equals to 2 pi radians and is equals to 360 degrees. We started off today's lesson with a refresher of the linear kinematics that we have learned previously. Today, we have explained to you what is angular motion and the quantities that we use to represent angular kinematics. All the formulas as well as the VT graph that you have learned for linear motion is fully applicable to angular motion. In fact, they are all the same. It is just a substitution of symbols. The velocity is now represented by omega. The displacement is now represented by theta. The acceleration is now represented by alpha. Hence, in theory, you are learning nothing new. It's just a substitution of the different symbols for the quantities.